What is this? Huh? What is this? What is this? For the plus sign looking like a charge. Because, you know why? Because quizzes are worth like 10% of your overall grade. We're going to do like tons of quizzes, a half a mark out of 35, 10% of that. When you consider we're going to be doing like 10 quizzes or whatever the course, it won't count for anything. But will you write your pluses like bigger and on the line? Yes, you will. Yeah? Hi.
I was in the bathroom. Sorry.
There you go. You keep it. Hole punch is here though if you want it. Keep it. They're just hole punching theirs. I should have hole punched them all before I handed them back, but I was not that clever. All good. Oh, yeah. You may or may not be here. I'm recording the lesson regardless, so we're good. Yeah. It's all good. So are you spending all your time running your tongue over your teeth? I remember that.
All right, thank you for letting me know.
So it stops at 50, and then we skip chapter 4, so we do like 22. You can't argue for it.
So you have, if you do not yet have the new blue book, make sure you go get that and an answer key. If you already have it, you do not need to do that. Okay. If you wish to rewrite this quiz, no problem whatsoever. You can rewrite it any day during flex time. Okay, just come on in. You know, if you're feeling ready, you could do it tomorrow. If you're feeling like you would like the weekend to study, you can study over the weekend and do it Monday or Tuesday. Okay? We are currently on page 114. 114. We're combining this with stoichiometry, but we will have a quiz on this section, the enthalpy. For the reactions, beige and blue together. Okay? Bond enthalpies Change in potential energy. Yes. Don't worry about that. Change in heat is not a thing. Just heat has a special heat. Shall we listen to the definition of heat? Okay. Here's the definition of heat. I'll even write it down for you. And this will explain why I keep saying just don't even talk about heat unless you're just kind of referring to it as like the heat term. Okay. Heat. H-E-A-T. The flow of energy from a body at higher temperature to one at a lower temperature when they are placed in thermal contact. Okay, so that's the official definition of heat. Yes? That is in the big black book, BLB, Brown, LeMay, Burston. But then they added a whole bunch of others, so now it's BLBMW. Okay, but anyway, that's our flow of energy from a body at higher temperature to one at lower temperature. So heat is not like a thing, it is a flow. It's a movement of energy from one thing at higher temperature to another thing at lower temperature. Alrighty? Yes. Is that a hand? Yes. We'll get to that. Okay. I want to finish with the definition. Okay. Now, enthalpy. Oh, this is even better. Enthalpy is a quantity defined, and you don't have to write this down. This is in the big black book. You can go and you can, open it up and take a screenshot of it or whatever you want. It is a quantity defined by the relationship H equals E plus PV. Ooh, isn't that awesome? Isn't that nice? Delta H, the enthalpy change, delta H, for a reaction that occurs at constant pressure is the heat evolved or absorbed in the reaction. Do you see why I'm not getting so excited about like giving you these definitions? Because they're like, what the hell, right? Okay. We will be doing some of this, but to be honest with you, AP does not really require you to understand these definitions. Okay, so that's why I don't focus on them a lot. So you should be thinking of enthalpy as the potential energy, and delta H as the change in potential energy from reactants to products. That's not a definition of enthalpy, but you can think of it that way. Okay, so how to think about delta H? Change in potential energy from reactants to products. If the reactants have more potential energy, then the reaction is going to be exothermic. If the products have more energy, then the reaction is going to be endothermic. Okay, and that's all you really need to know. Just go with that. Don't get too excited about the actual meaning behind them. I was just talking to Manning, who's in my regular Chem 11 class, but he was interested in orbitals, okay? And so I gave him this book and he started reading about the orbitals and he's like, it is really, really conceptual, isn't it? It's like it doesn't make a lot of sense. Like you sort of get this idea and then you don't. And so I was explaining to him that how I dealt with a lot of this stuff is I was like, okay, here's a concept and I don't understand it. And there is math involved in it. Like, so for example, in the orbitals, there is so much math involved in that. There's like pages and pages of math. I am never going to understand that math. My math brain is not that good. So what I do is I have this little box in my brain for, I just need to make an analogy for this that works for me. And then I'm going to go from there and I'm just going to be like, I'm never going to understand the math, because if I try to understand it at a deep level, I will just cause myself pain. Yes? So there's a little box in my head for things that are too complicated for me to understand right this moment. And then there's another little box for things that are too complicated for me to understand ever. And I've gotten really good at compartmentalizing them that way. A lot of things have moved from the I can't understand it now to I do understand it later. But there are some things that are still in that I am never, ever truly going to understand this. But I've got my little analogies so well in my brain that I'm okay with it. I am at peace with it. Yes? And just realize that as you go through first year university, second year university, you will be taking courses that are maybe not in your preferred stream, right? Like if you're going to biology, you're still going to have to take chemistry and physics, and you may not want all of it, okay? And you'll be like, okay, I'm just going to make a box to get myself through this, and that's how much I need to understand, and sometimes I just have to follow a process without understanding it. It's not ideal, no. Would I love to understand everything? Yes, I would, but I just don't sometimes. Yes? Well, I'm telling you, I will tell you, you only need to know this much. Okay, I will literally be like, you only need to know this much. Professors are not usually that nice, but you can kind of, you can get an idea from looking at old exam questions and stuff, like what are they actually asking me? And so, if they're never asking me to talk about, a reaction occurring at constant pressure and the relationship between that, the heat evolved there and the enthalpy, if they're never asking me a question about that, I don't need to know it. And I'm telling you, they never ask questions about that. Okay? So how to think about delta H? It is the change of potential energy from reactants to products. And we can calculate that. We are estimating it. One way of estimating it is to, bond enthalpies are one method of finding delta H for a reaction. Delta H reaction means delta H of a reaction. There will be other methods that we will learn later, okay? But this is one of them, and we'll actually do some comparisons between the two. So bond enthalpy, if you were really wanting to know what a bond enthalpy is, it is the energy used to break a bond. Or, and this is the best part, it is the energy that is released when a bond is formed. So either way, it doesn't matter whether you're breaking it and you had to put that amount of energy in, or whether you are forming it and that same amount of energy comes out, we are looking at the absolute value of that. Does that make sense? So it doesn't matter whether we're putting the energy in or getting the energy out, we look at just the absolute values. Okay, and then we say, were we breaking it? Okay, that required input, so that's positive. Was it forming? If that's the case, then it's output, it's negative. And then you just put your signs on. So here's a bunch of bond enthalpies. And I've sort of grouped them so you can see like single, double, triple, single, double, triple. What does it mean to have a single bond? One pair of electrons. Yes, what is a double bond? Two pairs of electrons. And what is a triple bond? Three pairs of electrons. So if you imagine that we have a nucleus and another nucleus, and we have two electrons in between, we will have a certain degree of attraction, yes? However, if we have a nucleus and we have a nucleus and we have more charges in between, 2, 3, 4, 5, 6. Whoa! Right? Thank you for providing sound effects for me. Look at the attractive force there. Is it bigger or is it smaller? It's bigger. The more charge you have, the bigger the attraction. Yes? And whose law does that work with? Coulomb's law. Coulomb's law. There's Avogadro's law. There's, when we get into the gases, there's lots of gas laws. There's Boyle's law, Charles' law, Gay-Lussac's law. Yes? No, I'm afraid not. It would be awesome if it were, but it's not. Did you have a question? Shh. Newton's law, yeah, the gravitational law. Yeah, and you know what? It's the exact same formula, except for you replace mass with charge, right? So yeah, if you've noticed that this is the gravitational law as well, except for that instead of mass, we have charge. So this is electrostatic attraction or Coulombic attraction. Now, most people call it electrostatic attraction. The AP people, chemistry people love to call it Coulombic attraction. I don't know why. Coulomb is a unit of charge, yes. Coulomb and joule. Oh, no, a coulomb is a unit of charge. Joule is a unit of energy. And if you put the two of them together, if you have your joules per coulomb of charge, then you have a volt. So a coulomb is like, oh God, what's the number? It's like something times 10 to the 34 electrons is a coulomb of charge. Okay? K is a constant. Okay? Q1 is charge 1. Q2 is charge 2. And R is the distance between the charges. Just for fun. It's like saying you have physics formulas and you spell formula with a PH, right? Gravitational is F is equal to G mm over R squared. So you place the, instead of a K, you have a G. Instead of the QQ, you have an mm. So yeah. It's a rebranded mass. Sure, let's say that. It's not at all, but that's okay. Okay, now, you do not need to memorize this formula, but what you need to know is that because the charges are on the top of that formula, if charge gets bigger, the force gets bigger. Because the distance is on the bottom of that formula, if the distance between them gets bigger, the force gets smaller. Does that make sense? Very much like gravity. Gravity, if you're up near the space station, it's not nearly as much as if you're here, right? And if you're on it, standing on a body of much less mass, like the moon, your weight is less. The force of gravity on you is less because the mass is less. So it's very much like gravitational law, okay? And that is why a triple bond is held together with so much more force, it takes a lot more energy to break it. Yes? A single bond has so many less charges in between that it takes less energy to break it. Okay? And that's what you'll see when you're looking at your bond enthalpies. You know, if we look at oxygen single bond versus oxygen double bond, which one has the greater bond enthalpy? The double bond. And if we look at, if we go over, here we go. If we look at our carbon-carbon single, double, triple, it goes small, medium, large. Yes, because the electrons that are shared get bigger and bigger, and the number of electrons get bigger and bigger each time. We can also look at the size, the distance between them. Now, the distance is regulated by the size of the atoms, okay? Now, carbon atoms are all the same size as each other, yes? Carbon atoms, all the same size. You can agree? Now, which one is the biggest atom? Hydrogen, fluorine, chlorine, or bromine? Bromine is the largest, and hydrogen is the smallest. So a hydrogen atom can get closer to carbon, yes, than the other one, than bromine, let's say, okay? Now, fluorine is a little different. I don't know why. Why is hydrogen so much smaller? Probably because the nuclear charge is so small. Like for hydrogen, you've only got a +1 charge in the nucleus that's attracting all those electrons. That's my guess as to why it sort of falls outside of the downward trend. But if we only look at these three, as this gets bigger, bigger, biggest, this gets smaller, smaller, smallest, okay? And hydrogen sort of falls out of the way because I feel like it's because its nucleus only has a 1+ charge, whereas fluorine is like +9, and there might be other reasons, but we'll not think about that too much, okay? Not right this moment anyway. See, I'm just putting that in a box, stuffing that in a box for a moment, okay? All right, So now that you know that, you've got all your table of bond enthalpies, and you can say every time I break one of those, if I break a carbon-carbon single bond, I am going to be putting in positive 348 kilojoules. If I form a CO bond, I'm going to be releasing 358 kilojoules, and so that's going to be negative. So this is just going back to what we did yesterday and just doing one more example because, you know, it was the end of the day and we might not have caught it. So let's do one more example. We have CH4 plus Cl2 gives CH3Cl plus HCl. And so we draw our Lewis structures, which again, I said later on we would, why is that thing in the middle of my page? That's okay. Apparently it won't go away. All right. If we draw our Lewis structures, we can see that 3 of the hydrogen bonds aren't changing. You'll actually often see people breaking all the bonds and then reforming all the bonds. You could do it that way. You could break 4 of these CH bonds if you wanted to. But then you would have to reform 3 of them. So I usually skip that step because that seems like extra work to me. But it's up to you, okay? In reality, you're really just breaking one hydrogen bond and one CH bond and one Cl-Cl bond. So you say to yourself, I have broken one CH bond and I have broken one Cl-Cl bond. And when my bonds are broken, that is energy which is absorbed, which makes these values positive. I have formed one CCl bond, and I have formed an HCl bond. I look up those values, and I get 328, but in this case, the bonds have been formed, so energy has been released, so my signs are negative. I add up all my absorbed energy, I add up all my released energy, and then I take the 2 of them and I add them together. And I get the overall reaction. I absorbed 656 kilojoules per mole and I released 759 kilojoules per mole. So overall, there was more release of energy than there was absorption. So overall, the reaction is exothermic, and delta H is negative 103 kilojoules per mole. Yes? Okay. More energy was released in bond formation than was absorbed by bond breaking. The ones that I ignored? Exactly. You could, if you wanted to, instead say, I am breaking all 4 of these, in which case you would take that value and multiply by 4, okay? And you would say, I am forming these 3, which is fine. I mean, there's nothing wrong with doing it that way. It's totally good. It's up to you, okay? Which way you choose to do it. Did you want to try some of the questions? Or we have one more example. Do you want one more example? Yes? Okay. So you have a choice. You don't actually have to write out all 5 O2s. You can just multiply. Okay, but I have written them out here for thoroughness just because it's helpful to me to be able to see. So if I have 5 O2s, then I am breaking 1, 2, 3, 4, 5 O double bond O bonds. If I have 2 HC triple bond CH, then I am breaking 1, 2, 3, 4 CH bonds. and I am breaking 2 C triple bond C bonds. So all of my breaking all together, like I said, you don't have to draw them all out as long as you're okay with just multiplying. I am breaking 4 CH bonds. So those are the blue ones, the light blue. Okay. We broke 4 of those. Ooh, maybe I should make this one a different color. I could make that one magenta. Okay. Ooh, I'm breaking 2 of those. I don't like that color, but that's okay. We're there now. And then I'm also breaking 5 O bonds. So I say I got 4 times 4, 1, 4, 2 times 8, 11. These are just numbers I've looked up on the chart. And 5 times 502. I get those. I add them all up. And when we get our total, we get 5,788. Yes. Oh, did I write it wrong? Probably a typo. Yeah, it should be 413. And if it's 413, then that value would be 4 times 413, 1652. Okay. So now we have 5784. Now what bonds are we forming? We're forming a whole schwack of C double bond O's. Yes. Did I write it wrong? 495. Oh, I don't know. I must have been using some other table. Yeah, that should be 5 times 495. Do you know what? Just like, yeah, just pretend that my values are correct. Pretend that they match the table. Can we do that? I'll go through and correct them all, but yeah. Okay, so this is also wrong, so I'll have to fix that. And there's some other things that are wrong. I think what happened is I had one table and then I had another table. C to 790, I don't know. I'll go through and I'll make this better, okay? Yeah. Yeah, there are, depending on which table you use, you will see different values because it also depends on what the neighboring atoms are doing. Like if you have something that's very electronegative attached to your C, which is then bonded to an H, it will make this bond less stable because the electron density is being pulled in that overall direction. Okay, so yes, different tables have different things. I thought I had done a better job of making it consistent, but apparently not at all. Okay, so I think I had used one set of values for one place and then I don't know. Anyway, I don't know what happened. It's just bad. Okay. Okay, so here we are. We can do it that way. Let's assume that my numbers are right. We end up with our positive value for the bonds being broken. We end up with our negative value for the bonds being formed. We add the two together and overall we get negative. Adriana. You would need to draw the structure. Yeah, so if you've done chemistry for a long time, you would look at C2H2 and be like, oh, that's an alkyne. Alkynes have triple bonds. Because carbon needs to have 4 bonds, and if I've only got 2 H's, then it has to triple bond with itself. Okay, but I will show you a way of drawing Lewis structures later. For now, they'll just be drawn for you, okay? And we'll, like I said, we'll get to it later. Once, it's a bit of a slog until you get used to the patterns, okay? Idamar, could you close our door for us, please? Thank you. Now, let's say you don't want to write out this every single time. You're like, oh my God, that looks like my work. I don't want to do that. Okay, you could, and this is the way that you'll usually see it in a book. You can write down, are you guys familiar with this symbol? Sigma. That is a capital sigma. And what does it stand for? Sum of. That's S-U-M of, not S-O-M of. S-O-M-E. Sum of. Some of them. All right. So you're going to take the sum of the enthalpies of the bonds broken minus the sum of the enthalpies of the bonds formed. You would still want to take a look at the actual structures so you could figure out what bonds are being broken and what bonds are being formed. Okay? And you could write it out like this. I actually don't find this to be any faster than doing it the other way, right? You'd be like, oh, I have 4 CH bonds. What's CH? CH is 413. I have 1 Cl bond that I'm breaking. What's Cl? I replace that with its value from the table. Okay. What am I forming? I am forming 3 CH bonds. Oh, those were yellow. Look at that. I'm forming 3 CH bonds. There we go. I'm forming 1 CC bond, or 1 CCl bond rather. And I'm forming 1 HCl bond. Okay, so it doesn't matter which way you show your work as long as you have shown like what's negative, what's positive, putting it all together. And make sure you have your units in there. Okay. And then we hit the end of the book, yeah. Okay. So you guys could do some problems here. No guarantees about the answer key because I don't know if I was using this table or I was using some other table apparently, but the process will be correct. The number should be relatively close. Do you know what I mean? I'm hoping that I use the same numbers, but I don't know for sure. Excellent. So we know where we're standing right off the bat. Okay, hang on a second. Let me grab this thing.
Yeah, we got the same thing, something like that. I'm going to do,
Yeah. Oh, and you know why? It's because my yeah. Yeah. This would be nice. We will have a quiz on this. Tuesday, Saturday. Like the bond enthalpy, so it'll be like one bond enthalpy question and then yeah.
just do that regularly. Really intense.
On beige and blue.
Oh, and then, what's our
Oh, let's see. Blue booklet. Blue booklet. You could read the introduction to stoichiometry. It's pretty straightforward. No, that's just a quiz. You can just take that. A little bit, yeah. I can do Yes. Yeah. How would we feel? Actually, I would feel more comfortable if our quiz was on next Wednesday on section 6.4, like enthalpy and bond enthalpies and all of that. Yeah? Yes. Combined test, yes.
Whatever you guys do, I'll do. Good review. Hey, you threw airplane to add it up. I love yeah. I'm serious.
And in fact, let's practice whispering. Oh, that would be awesome. Do you guys know how to whisper? I find that many students don't know how to whisper. If you can hear a tone in the voice, how is it whispering? There's no tone in the voice. Whisper. That's because I'm projecting you through. He can still hear me. Shocking because he's right beside me. Do you guys need to hear me right this second while I'm speaking with him about a question he has? No, so I don't need to talk this loud to him. Yeah. So if you just take atoms, it has mass. Now, if you have two verbs, yes, where would the masses like verb here and verb here? Where would this like be?
Oh, no, wait, I wrote QOA.
If I work hard, so we're going to do this with. Where's my other magnet? There. I need to bring in my better magnet. I'm actually thinking that